Hello, it's Dave Giles here for the next lesson of Cambridge International Education IGCSE Physics, and today we are looking at voltage and current characteristics, or we could say we're looking at non-ohmic conductors. So, first of all, we need to define what is meant by an ohmic conductor before we can look at non-ohmic conductors. Interpret voltage current graphs for ohmic and non-ohmic conductors. Describe key features of a non-ohmic conductor and apply knowledge of non-ohmic conductors to practical circuits. I've put as an extension, however, you probably would get a question like that at IGCSE, so maybe should not be an extension there. So assume that the key words for it there: voltage, current, ohmic, resistance, diode, LDR, which is a light-dependent resistor, and thermistor. Okay. So in an ohmic conductor, such as a resistor, so a resistor is an ohmic conductor, the current is directly proportional to the voltage. In other words, as the voltage doubles, so too does the current, and when the voltage or potential difference is zero, the current will be zero and vice versa. However, non-ohmic conductors behave a little bit differently. So ohmic conductors, we follow Ohm's law. Non-ohmic conductors, a little different. So an example is a filament bulb. So this is a filament bulb, the kind you might have in your living room, or probably more of an old-fashioned one that you might have had if you've got an old one in your living room. And all I want you to do is just calculate the resistance for each of these voltages. So the voltage being a control variable, not a control, the independent variable is the voltage. The dependent thing we're measuring is the current. So now we're going to work out the resistance. Okay, and I'll put the answers on, and you can see that in a bulb, as the current increases, the resistance also increases. And we're going to look at why in a second. But it can be shown in the graph. So you can see there, as the current increases, the voltage increases at a higher rate. Or you could say, as the voltage increases, the current increases at a lower rate. So you can see from this one here, if we've got voltage on the x-axis, that the gradient is getting less and less steep. So less current is flowing, or rather not less current. The current isn't increasing as much as the voltage. So that's because the resistance is getting higher. And now we'll look at why. So this links into a little bit of chemistry if you do that at IGCSE as well. It is in a metal, which is the most common conductor, you've got metallic bonding. So you've got a metal ions here, or positive ions. Then you've got electrons, which are free to flow. They're called delocalized electrons, and these are metal ions. The delocalized electrons are free to flow through the metal, so carry a current. And you can see here from this little GIF that the resistance is caused by collisions between the free electrons and the metal ions. So when it's a cold wire, the metal ions are still vibrating and still causing collisions. However, the hot wire, there's a lot more vibrations going on, so a lot more collisions between the electrons and the metal ions, so the resistance is increasing when it's hotter because of the extra vibrations. One small downside of this, I'll quickly point out, they've actually got the electrons bigger than the ions when, in fact, it'll be the other way around, and the ions will be significantly bigger than the free electrons. So which one has the most collisions between the ions and free electrons? The hot wire. Current is a flow of electrons, or charge, but it's pretty much always electrons. Was the result of more collisions in the hot wire, increased resistance, and reduced current. So that's why a bulb doesn't strictly follow Ohm's law, so voltage and current aren't directly proportional to each other. Next one we're going to look at is a diode. Now, the semiconductor allows current to flow in one direction. It's indicated by its symbol here. So this is an actual diode, and you can see it's black one end, and there's a short grey band at one end. And this here is the symbol for a diode. Sometimes you might see it with a circle around it as well. And this direction here means that current will flow. So if I have a positive current here, and it's the negative end, then current will flow. That's called the forward bias. Now, you don't need to know the term forward bias, but you might come across it, so I'll put it in here. Current will not flow in this direction, and this is the reverse bias. So if I have a positive current here and the negative end is there, current will not flow. So you can see here I've got a bulb. This is the positive end. It's in forward bias, so the bulb will light up. Now the diode's turned around or reversed. The cells, or sorry, battery, 6 volts, is putting the diode in reverse bias, so no current will flow, or very, very, very little. We'll assume it's 0. So if you plot current against voltage, what you'll see is in reverse bias, no matter how big the voltage is, you're not getting any current flowing. And then in the forward bias, you still need a small voltage across the diode around 0.4 and 0.7 volts, and then current will start to flow. So diodes have a very high resistance in one direction, the reverse bias, so current will not flow. And they have minimal resistance in the other direction, the forward bias, so current will flow that way. So why doesn't the graph start with the current from the origin? So it's like I said earlier, the diode will allow current to flow through it once it has a voltage across about 0.7. Again, that's a very rough figure. Once it has 0.7 volts across it, the current will start to rise. So is it an ohmic conductor? No. And that's because the current doesn't always increase directly proportionally with the voltage or potential difference across it. Next up, an LDR. LDR stands for light-dependent resistor. You don't always have the symbol, or it doesn't always have the circle around it. So it stands for light-dependent resistors. The greater the light which falls on the LDR, the lower the resistance, i.e. more current flows at higher light levels. And you can see here, as the light level or light intensity increases, the resistance decreases, and it follows this shaped graph. Can be used as a light detector. And some places where you might see that are alarm clocks, cameras, and probably the most common one is street lights. Some are on a timer, so they don't use an LDR. Some, if you've got somewhere where the timer gets dark, varies a lot, they may have a LDR on it, so it detects when it's getting dark and the light turns on. Now, a thermistor, this is the symbol here. You see it, so the resistance is dependent on the temperature. Our electrical component where the resistance decreases with temperature. This is the opposite effect to what we see in most other electric components, because like we said earlier, when we looked at the bulb, as we increase the temperature, the resistance got higher, but a thermistor is the other way around. So they're good at detecting temperature. So an example here would be some sort of greenhouse where the sprinklers turn on, or maybe a heater, or maybe something to cool it down, turns on depending upon the temperature. Other places are digital thermometers, fire alarm systems, which detect heat rather than actual smoke. Some do that, sorry. Circuit detectors and thermostats. So depending on whether you live in a hot or cold country, if you're using an aircon and you set it to 25 degrees, it'll adjust the output of the aircon unit depending upon the temperature in the room. Or if it's a heater, it'll do the same. If you've got some sort of electrical heating, you set it on if you've got a good one rather, and you set it to a certain temperature, then it will turn on or off when it goes. Sorry, it'll turn off when it goes above that temperature, and when it goes below, it'll turn back on again. Okay, and this is just a quick summary, which you might want to screenshot of what we've talked about so far. So we'll have a look at some paper 2 questions. Which circuit contains a diode connected in series with a fixed resistor? So we can see terminal's got diodes, C and D. However, D has got a variable resistor here. So the answer is C. Very easy question to start us off. So which one shows VI characteristics for a fillet, or IV rather, characteristics for a filament lamp. So we know straight away it's not I, it's not D. So we know it's got a curved kind of shape. And we also know that as the current increases, the resistance also increases. So in this example here, I've got, or rather say, as the current increases, the rate of the voltage increasing decreases. And from that, the one which basically has got a graph which shows, so if we do I over V, so one of these two, then the gradient should be getting less and, the resistance, start again for that one, is voltage divided by current. And that means that if we had the other way around, V on this axis, I on this axis, then the gradient should be increasing for that increased resistance. However, we've got it the other way around. So the gradient is proportional to the inverse of the resistance. So the answer is therefore A. Question 3. Which statement describes how a diode operates an electric circuit? So let's go through them. When the temperature increases, its resistance increases. That isn't true. The diode doesn't have a variable resistance in that kind of way. It's just that in the reverse bias, the resistance is almost infinite. When the current becomes too high, it melts and cuts off the current. That sounds more like a fuse. It only allows current to flow in one direction. That is true, but we'll just double check it's not D. It uses a low current circuit to switch on a circuit carrying a much larger current. That sounds like a relay, so the answer is C. Question 4. Pardon me. So this one's a little bit more tricky. A diode and a resistor are connected across a variable DC supply. Terminal X is initially positive and at their maximum value. The potential difference across X and Y is adjusted so that it changes as shown by the graph. Which graph shows how the current in the circuit from X to Y varies during the same time interval? Okay, so you can see here between X and Y, it starts with this end positive, and then it changes so the other end is positive after a while. So positive, potential difference, and then this end, and then negative potential difference. So when the potential difference at this end is positive, that means it's actually in reverse bias, so no current will flow. Then when it becomes negative and this end becomes positive, current will start to flow, and it'll flow in this direction from Y to X. So the answer is therefore D. And lastly, I'll say penultimately, one more after this, the diagram shows a light-dependent resistor connected in a potential divider circuit. The brightness of the light falling in the LDR is increased. Which row shows what happens to the resistance of the LDR and what happens to the reading on the voltmeter? So we talked about earlier as the brightness increases, the resistance decreases. So we know it's either A or B. If I've got less voltage here, that means I've got more voltage here instead. So the reading on the voltmeter is also going to decrease. So the answer is therefore A. And the last question, in which circuit do both the lamps light up? So we'll go through from A. So this is positive. straight away I can see here that that's not going to light up because that's in reverse bias. Starting here, that will not flow as well because, so no current will flow, no bulb will light up because that's in reverse bias. We go to C, positive here, it'll flow through there, it can also flow through there. So it looks like the answer is C, but we'll double check by looking at D. This end's positive, it'll get here, then it'll be blocked. So current will flow through the middle lamp, but it won't flow through the bottom lamp. So the answer is therefore C. And the last question we looked at before this was actually a question about a potential divider circuit. So that's an application which we haven't covered yet. However, that will be in the next lesson, which is on potential dividers, where we spend a full lesson looking at that. So I'll be posting a link in the description below soon. Thank you very much, and I'll see you for that lesson.